Alright, y'all. So in this second part of the video, we are going to be fully dedicated to exploring the properties of exponentials and logarithms. And this is going to be a lot of algebra, so it's a lot about solving equations and manipulating expressions. The properties of exponents we've already explored before. So for example, if I have two exponential expressions multiplying each other with the same base, then their exponents will add, right? Oh, let me do that. Their exponents will add. So for example, if I have x squared times x to the third, that is x to the fifth, because 2 plus 3 is 5. Or with an exponential, I could have 2 to the x times 2 to the y, and that would be 2 to the x plus y, and so on. So we have the product rule, the quotient rule, where if they divide, then they subtract, and the power of a power. So the idea that if I have an exponential and then there's an exponent on it, those exponents will multiply. So you see here that they've multiplied. So for example, if I have 2 to the power of x, 2 to the x, then to the power of y, that is 2 to the x times y. All right. So now we're going to look at the properties of logarithms, and I really strongly recommend that y'all take notes about these properties of exponents and the properties of logarithms, and just always keep those available when you're working with them. So the first one is the way that the product rule works for logarithms. So with logarithms, if I have two logs adding, if they're adding, then actually what happens is that the insides will multiply. I know it's kind of crazy how it works. If you want to see a proof of it, you can always ask me. But essentially, if two logs like log A and log B add each other, then that is equivalent to log A times B. So anytime logs are adding, you can always combine them. Similarly, if they subtract, so if I have log A minus log B, then those insides will divide. So I get log of A over B. So you can see here, log of m over n is the same thing as log of m minus log of n. And finally, this kind of crazy one that's super, super useful to us is the power rule for logs. Essentially, if I have a log of 2 to the x, for example, that is equivalent to x times the log of 2. Essentially, what's happening here is that the exponent can just go in the front. The exponent can just always go to the front of any log. So let's say I have the following expressions, and I want to simplify them to single term. I am going to keep available my notes about these properties of exponentials and logarithms in order to help me out with solving them. All right, so now I have the properties of exponents and the properties of logarithms to the right of my whiteboard in order to always be able to refer to those. So let's get started. Here I have an equation which actually might be familiar to you guys. Y'all probably worked with exponentials in this form in Algebra 2. But in case you didn't, let's go ahead and try to work on it and solving it. So I'm trying to simplify this expression into a single term. In order to do that with these exponentials, I want everything to be the same base. That way I can use my properties of exponents. So I noticed that this one is base 2, this one's base 4, and this one is base 8. Well, I know that 4 is equal to 2 squared, and 8 is 2 to the third. So what I'm going to do is I'm going to replace those with that. So I would have 2 to the x times 2 squared being raised to the power of x plus 1 all over 2 to the third. Now by using my exponent properties, the power of a power, I can see that this power of 2 and this power of x plus 1 will multiply each other. So I would get 2 to the x times 2 times x plus 1 is 2x plus 2 all over 2 to the third. when I simplify this further, exponentials which multiply by my properties will add. So that would give me 2 to the x plus 2x is 3x plus 2. However, I'm also dividing by this exponential. And when you divide them, they subtract. So what's 2 minus 3? Negative 1. So in the end, we get 2 to the 3x minus 1. And what's going to happen, y'all, is that when I'm solving equations, previously I couldn't have solved an equation which had this expression here that I started with. I would not be able to solve an equation which had that expression. But one that has this one right here, for 2 to the 3x minus 1, I actually can solve. All right, so we're going to go ahead and zoom in our focus on this second problem. So this is our first time using the properties of logarithms to simplify an expression. Now, looking at this, I have two terms. One log here that is natural log and being multiplied by 3, and another one here that is the natural log of x, and they're subtracting. So the first thing to notice here is that I actually I can't yet use the subtraction law. I can't use the law of logarithms that involves subtraction in order to say that this is ln of x minus 1 over x. I cannot do that. Okay, I cannot do this. The reason why is because this 3 here is still in the way. It's multiplying the ln. So in order to combine two natural logs, they need to have or just any two logs using these properties. They need to not have a coefficient. So how do we get rid of the coefficient? Well, we have a property of logarithms which involves coefficients. It is the power rule, right? So if I take my power rule and I apply it here, what I would see is that the 3 right there can go as an exponent on my inside of my logarithm. So this would rewrite as the ln of x minus 1 cubed minus the ln of x. Now I can use the subtraction rule and rewrite this as natural log of x minus 1 cubed over x. And what you'll notice here is that what I have here is the natural log is applying to this entire expression, okay? I don't have to write those brackets, but I write them there just so you guys can kind of see the distinction. So here's my final answer. ln of x minus 1 cubed over x. All right, so now we're going to do another one of these simplifying logarithms expressions. And here I have 3 times the log of a plus the log of b minus 4 log c. In this one, there's a couple things I could do, but first of all, I have this 3 kind of in the way, huh? Same with the 4. The 4 is in the way, just like we saw in the last one. So first off, I want to use my that power property, that power rule, to get rid of the coefficients. So with this one, it's pretty with the 4 log of c, it's pretty easy. It will end up being minus log c to the 4th, right? Because the 4 will go to the top. Now, what about 3 log a plus log b? What I could do is I could distribute the 3 first and then figure it all out. But I'm going to do it a little bit different because I see here that log a plus log b is inside the parentheses. And I know that that can combine from the product rule to make log of a times b. In which case, then it's just a 3 inside there. So I just got to use my exponent property again. And I apply the power of 3 to the inside. So watch this. What I get is log of ab to the power of 3 minus log of c to the power of 4. Notice that I took the power that I applied to AB and I raised the entire AB to the 3rd because the whole thing is being cubed, not just one of them, okay? In fact, this power of 3 technically distributes and becomes the log of a cubed, b cubed. So you can see that both terms inside got cubed. And then if it's minus log c to the 4th, that would be a division on the inside of c to the 4th. So in the end, I have the log of a cubed b cubed over c to the fourth. And that is my final solution. Excellent. Let's do one more of these simplifying log examples before we do anything too crazy. So here I have 3 ln of 2 minus 1/2 ln x plus ln of x plus 1. So let's see what happens here. I should probably get rid of my, my coefficients first. So I'm going to first get rid of my coefficients. So I'm going to put 3 in the power of 2 and 1/2 into the power of x. So I would end up with the natural log of 2 cubed. 2 cubed, that's 8, isn't it? I'm going to just write 8. So the natural log of 8 minus the natural log of x to the 1/2 plus the natural log of x plus 1. What you guys should notice here is that this guy here, the natural log of x to the 1/2, is subtracting, right? It's subtracting. Oops, that looks kind of messy. Notice that it's subtracting. So it's going to divide, right? So I would end up with, when I combine these, I end up with the natural log of 8, and on the bottom is x to the 1/2. And then ln of x plus 1 is adding, so it will multiply by x plus 1 on the top, right? So that's how I can combine my logarithms. Last thing we should do, x to the 1/2, I'd like to rewrite that as the square root of x. So this is the ln of 8 times x plus 1 over the square root of x. And I didn't really need to do that, but I just felt like it. Alrighty, so we've done a couple of these simplifying with the properties of logarithms. So now I want to show y'all why it is useful for us to be able to work with the properties of logs and exponentials in order to combine things. A big part of it is because it allows us to solve equations. So in this problem here, I'm going to be solving for n, the variable n right there. So if I want to solve for n, I need to work to get n on its own. The thing here is that n is actually a part of a greater term, a greater piece, this 2 to the power of 2n minus 1. So what I need to do is get that alone. Treat this essentially like a single variable. This blue circle is a single variable. If I had 4 times something plus 5 equals 29, y'all can solve that real easy, right? If I had 4x plus 5 equals 29, y'all can solve that extremely easy. You'd end up getting that x equals, we subtract 5, get 24, divide both sides by 4, you'd get x equals 6, right? Similarly over here, I'm going to subtract 5, get 4 times 2 to the 2n minus 1 equals 24, divide both sides by 4, and I get that 2 to the 2n minus 1 is equal to 6. Oh, dude, what do you know, man? Look at this. We have an exponential of base 2 and it equals 6 again. This is like our original exponential reasoning problem. So we need to use a log base 2. So I want to show y'all one way that I like to think about it when I'm doing algebra. I'm going to take this 6, I'm going to move it over a little bit. I like to think about it like I'm taking the log base 2 of both sides, right? Because I can do the same thing both sides, right? Even taking a log of them. And what happens? Well, log base 2 of 2 will actually end up canceling each other out. That would equal 1, right? But before I can evaluate that, I can use my power property, my power rule of logs, to take this exponent and move it in the front, right? Because this is a logarithm. And remember, the exponent inside the logarithm can move to the front. So what do I have? I have 2n minus 1 times the log base 2 of 2 equals log base 2 of 6. Well, log base 2 of 2 actually is just 1, so that will cancel out. And so I get 2n minus 1 equals log base 2 of 6. So I can solve that by adding 1 and dividing 2 over. So I get n equals log base 2 of 6 plus 1 all over 2. That's my n value. And you can evaluate that using a calculator and the change of base formula, right? So I want to leave that one up to you guys to try out to get you practicing with the change of base and evaluating logs and so on. So I'm going to leave this one here. All right, so let's try this solving equations problem where we've got some exponentials all equaling 0. Now this one looks super weird because you've got e to the 2x minus 4e to the x minus 5. It's like, what is happening here? Now there's a little trick to this problem. What if I use something that we call a u substitution? We call this a u substitution. What we do is this: we define a new variable. I'm going to call it u. I notice that in this expression here, I have e to the x occurring multiple times, right? I have e to the 2x and I have e to the x. I'm going to call that u equals e to the x. All right. So wherever I see an e to the x, I can replace it with a u. So for example, here, I would have minus 4u minus 5 equals 0. What about e to the 2x? Well, e to the 2x is equal to e to the x squared, right? By our exponent properties. So that means this is the same thing as u squared. Do you guys see how this can then be solved here with the u's? This is actually a really common strategy in algebra where to use this u substitution. The idea being, I see this and I recognize that it looks kind of like a quadratic. I saw that it had a 2, it had a 1, like a power of 1 and no power. So I thought it was like a quadratic, so I replaced it. And so what we see is that I can actually end up factoring this. That would factor into u minus 5 times u plus 1 equals 0. Well, I can then solve those. U is 5 and negative 1. But what was u originally? It was e to the x. So e to the x equals 5 and e to the x equals negative 1. How do I solve for x here then? I just have to do a natural log of both sides. The natural log of e to the x equals the natural log of 5. The natural log of e to the x is equal to the natural log of negative 1. And when I have natural log of e to the x, the natural log and the e cancel each other out. And I'm left with just x, right? So I know that x is equal to natural log of 5. And x equals the natural log of negative 1. Now this is a slight problem here. If you guys remember from our classwork that we did at the beginning of the week, we saw that natural logs can, the domain, like natural log of x must be greater than or equal to 0. We saw that. You cannot plug a negative number into a natural log. Because if you think about it, right, looking at this expression here, no matter what x equals, I will never get a negative number. If x is negative 100, e to the negative 100 would just be, e to the negative 100 would just be 1 over e to the 100, which is a small number, but it's still bigger than 0. So essentially, this solution here is not legit, but the solution that x equals natural log of 5 is. So that's a real big algebra problem involving exponentials. Now let's take a look at one involving logarithms a bit more. I'm gonna go ahead and lasso this stuff down lower to get it out of our way. So here I have 3 log base 2 of 3 to the x equals 9. All right, so we can solve this by dividing both sides by 3. I get log base 2 of 3x equals 3. Use the decoder ring. 2 cubed equals 3x. which 2 cubed is 8. And then I just divide both sides by 3. So I get x equals 8 over 3. That one was pretty easy, huh? We could have solved this before this video. All right, guys. Well, here's the last one, and this is the end of the video. Here's where we see the properties of logarithms come in handy for solving an equation. So I have ln of 2x minus 3 plus ln of x plus 2 equals 2 ln of x. To start off, I want to, as we have done when we solved equations before, I want to get everything equal to 0. So I'm going to subtract that 2 ln of x over to the left-hand side. So I would have ln of 2x minus 3 plus ln of x plus 2 equals, not equals, minus 2 ln of x equals 0. Now I can work to combine these guys. I know that if I have a 2 times the ln, it makes ln of x squared, right? So, and then I also know that these two natural logs, if I have two logs adding, the insides will multiply. So I get the natural log of 2x minus 3 times x plus 2 minus the natural log of x squared. Well, what happens when I subtract logs? Their insides divide. So I get the ln of 2x minus 3 times x plus 2 all over x squared equals 0. Alrighty, now can we solve this part? We would use our decoder ring, right? So e, because that's the base of a natural log, e to the power of 0 equals the inside. What is e to the 0? It would be 1. Anything to the power of 0 is 1. So now I know that 2x minus 3 times x plus 2 over x squared equals 1. So how do we solve this? At this point in time, guys, this is a rational equation. We can solve this just like we were solving those other rational equations. We want to get rid of the denominator by multiplying by it. So I'm going to multiply both sides by x squared because that will cancel out here. In the end, I can get that 2x minus 3 times x plus 2 using double distribute would be 2x squared plus 4x minus 3x, so plus x, and then minus 6 equals x squared. All right, all I have to do is subtract x squared from both sides and solve. So I get that. So I get that x squared plus x minus 6 equals 0. I factor it to x plus 3 and x minus 2 equals 0. And therefore, x equals negative 3 and 2. Now, just like when we were solving rational equations before, we want to actually check our solutions to see if there's any extraneous solutions, right? If any of these cause problems. So when I plug negative 3 back in, what happens? I would actually get some negative logarithms, right? So I would get the ln of 2x minus 3 when x is negative 3. 2 times negative 3 is 6. Minus 3 is negative 9. So I get the natural log of negative 9. And remember, we said that negative numbers cannot be plugged into a natural log. So therefore, I'm going to get rid of that solution of negative 3, actually. What about 2? Is 2 okay? When I plug 2 in to 2x minus 3, I get a positive because 2 times 2 is 4, minus 3 is 1. When I plug in 2 in here, I get 4. When I plug 2 in here, I get 2. So they're all fine. So the true solution is x equals 2. Now that is solving equations involving logarithms. So you can see that it can get a little bit complicated, but really it's just adding another step to what we already were doing. Essentially, combining the logarithms is the new part, But then once you've gotten rid of the logs using our log rules, we have ourselves a very standard rational equation. And that can be solved using some careful algebra.